Now off to our fifth paper, Rethinking Personalized Ranking at Pinterest, an end-to-end approach. Jiajing Shu will be presenting.
Yeah, thanks for the intro, Alan. And hi, everyone. This is Jiajing from Pinterest. I'm here to present our paper on behalf of my co-authors. And first off, I'd like to thank all my colleagues who worked on and helped with this project. This work would not have been possible without their contribution and support. Here's the agenda for the talk. I'll walk you through the background needed to understand the motivations behind this work. Then I'll dive into the training, serving of the model, and talk about the findings we discovered in experiments. In case some of you are not a Pinterest user, I'll briefly introduce what Pinterest is. Pinterest is a platform to find inspirations and the tools to realize that in one's life. People come to Pinterest to find inspirations in all forms, from finding what to eat for lunch, what hairstyle to have, to planning their wedding or remodeling their home. The basic element on Pinterest is a pin, and this is an example of a pin. A pin is nothing more than a visual bookmark containing an image, URL, and some descriptions. We allow user to curate and annotate the pin object. And of course, we also know where the user saves the pin to and how user engages with the pin, such as save, close up, or click through. And the magic happens when user saves the pin to a board. In this example, we know the pins from this board are all about chairs. And secondly, we know the user is in the market of buying a chair. So imagine this is happening in a very large scale. And there are many ways users discover pins on Pinterest. The first one is through home feed, where it shows user the recommended ideas based on their interest. Next is the search feed, where you can find ideas when you have a keyword in mind. And the last one is what we call related pins, where you close up on a pin and we will populate similar pins to the close-up pins. Not surprisingly, we built recommendation systems to populate the content in these feeds I talked about earlier, both organic content as well as promoted content, as known as ads. And each recommendation system typically have a candidate generation stage and a ranking stage to ensure we can find the very best set of pins to show to the user. And the machine learning model behind this recommendation system leverage all kinds of signals, like the ones that represent user intentions, the ones to describe text or visual aspect of pins. And the focus of this work is on the user intention signal. So recently, transformer-based sequence modeling starts to gain popularity to model user intentions. But the complexity of the model quickly hits infrastructure limitation in terms of how long the sequence can be. And in this work, we'll break down the user intentions into two parts. First, long-term interest that doesn't change from day to day. And second, the short-term intention, which what the user plans to do at the moment. And we adopt very different strategy to model them separately. So for the long-term interest, we propose the end-to-end learned user embeddings through sequence learning called Pinformer to encode users' long-term interest. And for the short-term intention, we learn directly from users' real-time logging with a transformer encoder. And this has led to great improvement in understanding user intentions. Now I'll dive into the details. So let's start with modeling the long-term user interest. We consider a user's engagement sequence from past year. It contains actions from different surfaces. It can be search, home feed, and it can also contain both positive actions like click, saves, as well as negative actions like hide. And in this work, we limit actions to be the user engagement with pins, including pin saves, clicks, reactions, and comments over the past year. So let's say this dashed line is the current timeline and separates the past, present, and future. So we want to encode the user's history and use it to predict their future actions. And more specifically, our goal is to predict users' long-term interests so that we can retrieve all positive user actions in the next 14-day window. Not hides, we only want to predict positive actions such as repings, clicks more than 10 seconds, etc. So the intuition here is that the model should not just capture users' next actions, but capture users' broader interests. And this is the main contribution and differentiates this work from any previous work. So for feature representation, to encode each action, we use pin stage, a pin embedding developed using graph neural network algorithm to represent the content of the pins. We also have embedding lookup tables for the types of action and the type of the feed. We also have some information about the duration of the action, as well as the time since the last action. The time features are encoded using sine and cosine transformations. The transform feature are then projected into some hidden dimension and then pass through a transformer. At every time step, we obtain a user embedding. One thing to note here is that at each time step, user can only attend to the past, present, not the future. This enforces causality, so that user takes sequential actions. Current actions are not influenced by the actions from the future. Similarly, we have some time window positive examples. 28-day time window in this example. For each example pin, we transform the associated pin stage embeddings and feed that into the loss function. And we introduced a new loss function called dense or action loss. From every user embedding at each time step, we want to predict all the action the user will engage in the next 14-day window. This forces the embedding to be stable and capture users' long-term interests. This also makes the problem more computational trackable since we can sample that down. So overall, this is how we train the pin informer end-to-end straight from user action logs. Next, let me talk about how we learn short-term user intention. So what motivates us is twofold. First, since pin informer captures users' long-term interests, it's relatively stable. It is inferenced on a daily basis, which means it doesn't cover what the user has done in the current session or past day. And second, for the most recent actions, we want to co-learn the relationship end-to-end with the ranking objectives. Can be organic engagements or ads engagement. So we collect users' past actions from real-time logging and represent each action with 4 features: pin stage embedding, as I mentioned earlier, action timestamp, action type, and action duration. These features are then passed through a self-attention block and then feed into a transformer encoder. Here, we apply random masks to the real-time sequence. The reason is doing so prevents the ranking model to react too aggressively to the user's last action, and thus recommends pins from the same category repeatedly, which is not a very desired user experience. Okay, so put the two components together, we made the changes highlighted in red to a typical ranking model here at Pinterest. The ranking model is usually a multitask learning model that output multiple predictions for different actions simultaneously. So let me talk about the serving. So when we first tried to serve this model online, we quickly noticed that the additional components have increased the model complexity as well as latency substantially. And natural solution is to switch GPU serving for these models. However, naive out-of-box GPU serving is actually very slow. Here's a screenshot of the profiling. We see a lot of overhead from many small operations, causing the GPU to have very low utilization. To improve this, the team has done extensive optimizations, such as reducing number of small operations, consolidating embedding lookups, leveraging CUDA graph to convert the model inference into a static graph. With all the above optimizations, we managed to improve the GPU utilization significantly. From the post-optimization profiling screenshot here, we can see that there's very little GPU idle time. And this table summarizes the GPU serving stats before and after the infer optimizations, comparing to a prod model served with CPU. So without the optimization, when we serve a model that is 30 times bigger with GPU, latency actually increased by 3 times, and the throughput dropped by 76%, which leads to a much larger infer cost. With the full optimization turned on, we managed to serve a model that is 77 times bigger with 30 times lower latency and 20% more throughput. In return, the infer cost is actually lowered by 20%. Great, now that we've addressed the serving challenges, we can start doing some online experiments. And we actually have done some extensive offline analysis in the paper, so please check that out if you're interested. And here, I'm just showing the online experiment results in both organic and ads application. And in both settings, we have a machine learning model to determine the ranking of organic or promoted pings. The evaluation metrics are organic repings and ads CTRs, respectively. And we compare the model with pin informer only, pin informer, and real-time together to a production model. As shown here, capturing user long-term interest with pin informer has significantly improved the metric. And with the additional real-time sequence to capture the short-term user intention, it lifts the gain further, as much as 12.5% increase in organic repings and 14% increase in ads CTR, which are huge to top 5 business metrics. So to conclude the talk, we find end-to-end learning from the raw logs is crucial for capturing user intentions. And by decomposing the user intentions into long-term and short-term, it allows us to be more creative to model them separately. And finally, a better understanding of both long-term and short-term user intention has greatly improved user experience at Pinterest. And that concludes my talk. And so thank you for your time. And please feel free to reach out for any questions.
Thank you. There's quite a lot of questions. I don't think we'll have time for all, but let's kick off a few. Is there a performance decay on the 28 days prediction when it is further into the future?
A performance decay comparing to...
So when you try and, if you would predict further into the future than the 28 days?
I see, compared to maybe 14 days? Is that the question?
Let's see.
Yeah, in general, that's the setup, and we've tuned that parameter a little bit. And in terms of model performance, actually, the longer time window helped the final application, if that's the question.
All right. Okay, let's go to another question. Given that the intent is to model long-term user intent, do results fluctuate across daily inference runs, and are they expected to vary?
I see. So there's some fluctuation. I mean, it depends on the user behavior in the past day, but we find it pretty stable. But we're still doing the daily inference.
Okay. There's questions both on cold start users and super heavy users. So for instance, do you downsample super heavy users?
I see. Yeah, in the data preparing stage, we actually do some sampling to make sure it's fair for to cover both spectrum. Yeah.
Okay. Are there any trainable weights to balance long-term signal and short-term signal?
That's a really good question. At this point, we leave it to the final engagement model, the larger model to learn that balance. And we're not tuning it specifically in the model, but we do have in the recommendation system at last stage, there's a utility function stage. So sometimes we do add weights there to tune the desired behavior for the model to present the right content to the user.
Okay. And last question, what's the baseline algorithm in the A/B testing?
I see. Yeah, so baseline is actually we thought it was a pretty good baseline. Like, you know, a team of smart engineers have optimized it for several years, right? And we didn't expect such a big a lift, but it turns out modeling user intentions really well is actually crucial for better user behavior, experience.
Okay.
Yeah, the baseline is actually very strong. It was a very heavy neural network model.
All right. Thank you.
Yeah, thank you. Thank you for all the questions.
Right.